So now we're going to look at how do we work out the critical values? What's the argument? What's the reasoning for the way that we're going to calculate those critical values? So let's just have a quick recap. We said we're looking at this is the population of students at Cal State Fullerton. We want to find out on average how long they spend studying, and we hypothesized that the status quo, the way things have been for a while, what we think the answer is most likely to be is 4 hours a day. And we're going to use a sample to test that. The result to our hypotheses test is either to not reject the hypothesis or to reject the hypothesis in favor of the alternative hypothesis. And the alternative hypothesis is either HA or H1. And the alternative hypothesis is going to be that students do not study for 4 hours a day. It's going to be the exact alternative or exact opposite to what we have for the null hypothesis. And the way we do that is, remember, we're going out, we're going to choose a sample, work out the sample mean, and if the sample mean is pretty close to the population mean, in this case it's the exact same figure, we're going to say that's close enough to agree with it, and we're not going to reject the null hypothesis. If on the other hand we choose a sample of students who end up studying for an average which is very different from the 4 hours that our hypothesis is saying, supposing they're studying for an average of 16 hours, that's way different. That is just way different from our hypothesis, causing us to reject our hypothesis and probably be more in agreement with the alternative that students do not study for 4 hours a day. The samples that we choose are actually called test statistics because statistic is just a number and it's a test statistic, it's a test number. It's something that we're using to test the hypothesis. So these sample means are called test statistics. Now, from earlier work we did, we looked at how we can set up the distribution of estimates of the population mean. And the way we did that, we'd pick a sample of students, work out what the sample mean is, and we'd plot it. Take another sample of students, work out what the mean is and plot it. Another sample, work out the sample mean, and we keep on plotting all the sample means on here. And we said that the resulting distribution is likely to come out to be a normal distribution. And we could actually do quite a bit of work with it. Now, in this case, let's assume, this is the argument for the critical value, let's assume that the average amount of time that students spend studying really is 4 hours a day. So let's put it in here. This is assume, well, we don't know this in reality, but let's just assume that it really was 4 hours a day. And all these other figures in here are just estimates of the real figure. Now, there is a possibility that even though this figure of 4, students really do study for 4 hours a day, our original assertion was correct, that really students do study for an average of 4 hours a day. There's a possibility that we choose a sample such as this one down here, which is very different from the 4 hours a day that that is not only the correct figure, but we actually hypothesized the correct figure. 16 hours a day is going to be way out here. And it's probably going to be too far away from the mean to agree with it. So this sounds like a problem. The problem is this. Even though we've come up with a correct null hypothesis, we've actually chosen a sample that does not agree with the null hypothesis. Now, the chances that this happens is very slim. There's not much chance that we're going to find a group of students that actually study for an average of 16 hours a day. And yet that possibility exists. And if we happen to choose that as our sample of students to test our hypothesis, it will lead us to reject our null hypothesis, which is in fact true. So there's a problem with hypotheses testing, which we know about. In fact, we can make errors when we do hypotheses tests, and this type of error is known about. We actually call it a type 1 error. So let's see that. So a type 1 error does exist. A type 1 error occurs when you choose a correct null hypothesis, but you actually reject it. So in this case, it could be that students really do study for 4 hours a day, but I was unlucky enough to choose a group of students for my sample that actually study for 16 hours a day, an average of 16 hours a day, causing me to believe that my assertion is wrong, and I can reject a true null hypothesis, and that is a type 1 error. A type 1 error will reject H0 when it is likely to be true. There you go. It says true. Okay, so that's we have to now figure out that this type of error exists. And by the way, we actually give it a title, which is alpha, which I'll tell you about in a moment. So we can reject a null hypothesis which is in fact true. We can't avoid that. So the issue then becomes, how much risk are you prepared to take in making this mistake of rejecting your null hypothesis when it is in fact true? Now, typically people say around 5%. I'm prepared to take a 5% risk in rejecting my null hypothesis when it's true. Some people say I'll take a 1% risk. Some people say I'll take a 10% risk. But most people say they're prepared to take between a 10 and 1% risk of rejecting a null hypothesis when it's true. But let's just say, let's go with 5%, somewhere in the middle. So let's say we're prepared to take a 5% risk of rejecting our null hypothesis when it's true. So alpha, in that case, would be set equal to 5%. When is it that we reject a null hypothesis when it's true? That's when we pick a sample of students that actually studies for an amount of time which is far in excess of the mean in either direction. It's very, very different from our hypothesized mean. So, well, if I'm prepared to take a 5% risk of rejecting the null hypothesis when it's true and making a type 1 error, I will set these regions here, these red regions here, I would set them equal to 5%. That is 2.5% here. And likewise, 2.5% here. And that actually means that my middle bit in here is 95%. So this region in here corresponds to 95% of my estimates. And I can work backwards now. If I know this is 95% and I know a lot about sampling distributions, I can now actually go back and work out what this point is here and what this point is here, and they will be my critical values. You may say, why don't we set the probability of making a type 1 error to 0%? That sounds great. That would mean that these red rejection zones, these red zones on the edges, would be equal to 0. So basically we'd have a 100% green zone in the middle and no red zones. So that would be great. when the null hypothesis is true, any sample we choose is going to be deemed to be close enough. There will be no red zones. It would only be green zones. But the problem with that is we don't know for sure if our null hypothesis is true or not. So the problem with that would be if I have no rejection zones here and all I have is a green do not reject zone because I wanted to accept only a 0% chance of rejecting it, the null hypothesis, if it was true. The problem is when the null hypothesis is not true, if there are no rejection regions, you will end up not rejecting a null hypothesis which is wrong. So that would lead to a type 2 error. Now, we don't say too much about type 2 error in this course, other than to make you aware of what a type 2 error is. That's a type 2 error. Sorry for the writing, guys. I'm new to this. And the type 2 error has the symbol beta. And that is when you fail to reject or you do not reject. You do not reject H0 when it is wrong, when it is false, when it is false. So now, what I can do is move down here a little bit just to... What we can do is work backwards to actually work out what these critical values are. I'm just going to come through here. This is one critical value in here, and this is another critical value in here. And in fact, let me just draw it again down here. It might make it a bit easier. These are your critical values, one here, and this is your mean, your hypothesized mean. Let's call it mu of H0. So mu of H0 in our case is the mean up here. Mu from H0, mu of H0, we just put the H0 here. So mu of H0 is 4 in our case. So mu of H0 is just the hypothesized mean. Remember, this is going to be in here, the do not reject zone. So this is do not reject H0 zone. And then we have the reject H0 zone down here. And the reject H0 zone over here. And the critical values, well, basically, if I want to make the middle region 95%, that region is 95%. I have to work out how many standard deviations I need to move away from the mean to achieve that. And basically, we know that's about 2 standard deviations according to the empirical rule. But so it's going to be, say, this side's going to be the mean plus 2 standard deviations, but it's not exactly 2 standard deviations. It's z of alpha over 2, or in this case, z of 2.5, that's the number of standard deviations. And so that's how many standard deviations, it's approximately 2. And what are the standard deviations for x bar? Well, when we know the population standard deviation, the number of standard deviations or standard errors is going to be sigma over the square root of n. So this is the raw form of working out the critical value. That 4.18 we had in the previous section, and in this case the 3.82 are calculated like this. And this doesn't seem like much of a surprise to us, given that we've just finished looking at confidence intervals. Sorry, this is a minus. Let me just go back there. Dropped all over the place. This is going to be, let's just get the eraser here. And this is actually going to be this is going to be minus z of 2.5%, the number of standard deviations or standard errors, sigma over the square root of n. So this is how you find out the lower critical value and the upper critical value. And these look very similar to the formulas that we use for the confidence intervals.